This is our planet Earth, vibrant, dynamic, and teeming with life. It's a world unlike any other we've found so far, the only known place in the universe where life not only exists, but thrives in astonishing diversity. What makes Earth so uniquely suited for life isn't just its perfect distance from the sun or the stability of its magnetic field. Perhaps most crucially, it's the thick atmosphere that envelops the planet like a protective blanket. From the vantage point of the International Space Station, we can see this invisible shield, clearly a transparent layer of mixed gases held tightly by Earth's gravity. This is our atmosphere, composed mainly of nitrogen, oxygen, and argon, along with trace amounts of carbon dioxide and other rare gases. It's this delicate balance of gases that makes the air breathable and the climate stable. As we rise from the Earth's surface, this atmosphere is divided into 5 distinct layers based on altitude, each with its own role in protecting and shaping life. The lowest layer, known as the troposphere, extends about 12 kilometers above sea level and is the densest part of the atmosphere. It's where clouds form, where rain and snow happen, and where all weather phenomena take place. Above that lies the stratosphere, reaching up to around 50 kilometers. The air here is thinner, but it houses a crucial feature, the ozone layer. This concentrated band of ozone molecules absorbs harmful ultraviolet radiation from the sun, acting as a natural shield that protects life below. Climbing even higher, we enter the mesosphere, stretching up to about 85 kilometers. Composed primarily of nitrogen and oxygen, this layer experiences rapid drops in temperature with altitude, which drives strong vertical air movement. Beyond that is the thermosphere, which reaches up to 800 kilometers above the Earth. Here, the air becomes highly ionized due to intense exposure to shortwave solar radiation. This region includes the ionosphere, where breathtaking auroras paint the skies with color near the poles. Finally, we reach the exosphere, the outermost layer of our atmosphere. Though generally considered to begin around 800 kilometers and extend to about 3,000 kilometers, scientists have detected traces of gas molecules at altitudes as high as 22,000 kilometers. So, in a strict scientific sense, the boundary of our atmosphere is far more diffuse than we once thought. The upper boundary of Earth's atmosphere is still something of a mystery. Although the atmosphere is made entirely of gases, its total mass is astonishing, around 55 quadrillion tons. Most of these gas molecules are held tightly in place by Earth's gravity, with the vast majority concentrated within the first 20 to 30 kilometers above the surface. As you move higher, the influence of gravity weakens, and the atmospheric particles become increasingly sparse. In fact, physicists have found that hundreds of thousands of tons of gas escape from the upper atmosphere into space every year. This slow but steady loss has been happening for billions of years, which naturally leads to a question. If Earth has been bleeding atmosphere for so long, why hasn't it vanished or even thinned noticeably? The answer lies in Earth's ability to continuously replenish its atmosphere. Every year, new gases are produced through ocean evaporation, biological activity, and volcanic eruptions. Even something as simple as the gas you just exhaled contributes, in a tiny way, to the planet's atmospheric balance. This constant give and take between what the Earth loses and what it regenerates creates a dynamic equilibrium that has kept our atmosphere remarkably stable for billions of years. Now zooming out into the vastness of space, we find a universe filled with all kinds of celestial bodies. Astronomers classify any object that generates heat and light through through nuclear fusion as a star. Objects that orbit these stars, whether rocky or gaseous, are called planets, with smaller or irregular ones further categorized as dwarf planets or asteroids, depending on their size and orbital characteristics. But there exists a strange and awkward in-between category of celestial objects that are neither stars nor planets. These bodies fall in a mass range somewhere between the heaviest gas giants and the lightest stars, typically between 13 and 80 times the mass of Jupiter. Because of their immense mass, their internal temperatures far exceed those of ordinary planets. Yet, despite this heat and density, their cores still don't reach the threshold needed to ignite hydrogen fusion, which is the hallmark of a true star. However, they're just energetic enough to spark lighter fusion reactions, like those involving deuterium or lithium. This makes them celestial misfits, too massive to be planets, not massive enough to be stars. Astronomers call these objects brown dwarfs. Most of the brown dwarfs we've discovered so far are about the same size as Jupiter, but vastly more massive, because of their cooler temperatures and the fusion reactions that do occur inside them. They often appear as dim orange or reddish objects when viewed through telescopes. Back in 2013, astronomers from the University of Pennsylvania made an exciting discovery using NASA's Infrared Space Telescope, WISE, roughly 6.5 light-years away in the direction of the Vela constellation. They identified a binary system made up of two brown dwarfs, a failed pair of stars known as WISE 1049 to 5319, or more formally, Lumon 16. To this day, it remains the closest known brown dwarf system to Earth. Each object in the pair has a mass about 30 times that of Jupiter, and their outer layers are shrouded in cloudy gas bands that emit a faint reddish glow because of how nearby they are in astronomical terms. Lumen 16 has become one of the most closely studied systems of its kind. Today, astronomers understand that brown dwarfs are essentially failed stars. In simple terms, when a cloud of interstellar gas and dust begins to collapse under its own gravity, it sometimes doesn't have enough mass to trigger the fusion reactions that power real stars. Without sufficient pressure and temperature at the core, hydrogen fusion never ignites, and instead of becoming a full-fledged star, the object becomes a brown dwarf. This is why scientists refer to them as failed stars. They started the process, but couldn't complete it. Now, moving from failure to fury, there's another phenomenon in the universe that's both spectacular and terrifying: the supernova. A supernova is one of the most violent events in the cosmos, a massive, stellar explosion that can outshine entire galaxies for a brief moment in time. Throughout human history, ancient records have described mysterious new stars appearing. In the night sky, what we now understand was supernova. Thanks to modern astronomy, we now know there are two main ways a supernova can occur. One involves a white dwarf, dense remnant of a smaller star, which gains enough mass from a companion star to ignite carbon fusion in a runaway reaction, tearing itself apart in a blinding explosion. The other happens at the end of a massive star's life, when its nuclear fuel is exhausted and it can no longer resist the inward pull of gravity. The core collapses suddenly, triggering a Type II supernova. In both cases, the result is catastrophic. A star that explodes in a supernova might leave behind a dense neutron star or, in some cases, collapse entirely into a black hole. A supernova may last only a few seconds, but in that moment, it can release as much radiation energy as the sun produces over its entire lifetime. If such an explosion occurred close to our solar system, the effects on Earth would be devastating. We would witness what looks like a second sun suddenly appearing in the sky, blazing white. But it's not just the visible light we'd need to worry about. It's the invisible X-rays and gamma rays that would bombard our planet. These high-end particles could tear apart the ozone layer, damage all living DNA, and cause fatal levels of acute radiation sickness across the biosphere. Fortunately, the solar neighborhood is relatively calm. There are no stars close enough to Earth that are expected to go supernova anytime soon. Astrophysicists do keep an eye on Betelgeuse, a red supergiant about 640 light-years away, which is likely to explode within the next million years. But even if it does, the blast, while dazzling, wouldn't reach Earth with enough force to threaten life here. Humanity's desire to explore the unknown has always been a powerful engine driving technological progress. Since World War II, the rapid development of rocket technology has pushed the boundaries of space exploration, allowing us to send probes far beyond Earth and into the vast, uncharted depths of interstellar space. Among all the probes we've launched, the Voyager spacecraft stand out as the most iconic. These two sister probes were part of a bold mission to study the outer planets, but they ended up becoming something much greater. The farthest traveling man-made objects in human history, launched in 1977, Voyager 1 and Voyager 2 have been flying through space for 48 years. Voyager 1, the more distant of the two, is now more than 24 billion kilometers from Earth and still moving deeper into interstellar space, so far that it has officially crossed the boundary of the solar system. If it continues on its path, it will take tens of thousands of years to reach even the nearest star system. But as incredible as their journey is, it's not just the distance that has captured public imagination. What fascinates many people even more is what the spacecraft are carrying, a pair of golden records designed to introduce humanity to any intelligent life that might someday encounter them. At the beginning of the Voyager mission, a team led by renowned astronomer Carl Sagan proposed the idea of creating these records. Their goal was both scientific and symbolic, to offer a message from Earth to the cosmos, a kind of time capsule for the stars. The result was to phonograph records, each coated in gold, containing a rich collection of information about our planet and our species. These records hold 115 images depicting life on Earth, greetings in 55 different languages, diagrams of the human body, recordings of nature sounds, and selections of classical music. Scientists even included the precise location of Earth in the galaxy, marked using the positions of 14 nearby pulsars, as a kind of cosmic return address. With these golden records, the Voyager spacecraft set out into the void, not just as instruments of science, but as messengers of human civilization, carrying with them the hope of someday connecting with life beyond our world. However, not everyone agrees this was a wise idea. Some scientists have raised concerns that broadcasting our existence to the universe could be dangerous. In recent years, Chinese author Liu Cixin's sci-fi novel The Three-Body Problem has popularized the concept of the dark forest theory, which suggests that revealing our location to alien civilizations might invite disaster rather than friendship. And to be fair, that concern isn't entirely without merit. After all, we have no way of knowing whether any extraterrestrial beings out there would be peaceful or hostile. But others argue that space is so vast and the odds of detection so small that the risk is negligible. Even Voyager 1, traveling at tens of thousands of kilometers per hour, would still take about 40,000 years just to reach the nearest star. Carl Sagan himself didn't believe Voyager's message would ever actually be intercepted. To him, the golden record was more of a symbolic gesture, a hopeful, poetic attempt to say, "We were here. It may never be found, but the act of sending it is part of what makes us human."